Okay, now we're talking about electric charge. We're back to electricity, and we're going to start talking about electrostatics. Electrostatics is static electricity, just like it sounds. Static means stationary. So now we're talking about things moving, and we're usually now talking about insulators and stuff like that, although we'll throw in some conductors, so we'll go on to it. Now, first of all, we have to kind of a quick review. Atoms have a nucleus which has positive and neutral things in the middle, and around it it's got electrons. They're orbiting at distinct energy levels. They have distinct amounts of energy, and more on that later in other courses. The key thing to understand is electricity is really nothing more than the movement of electrons. That's all that can move. Protons can't move, neutrons can't move unless the entire object moves. But I can transfer electrons from one thing to another. If an object gains electrons, it's going to have a net negative charge. If it loses electrons, it's going to have a net positive charge. All atoms start out neutral. They may have 1 trillion positives and 1 trillion negatives. It's when they gain or lose negatives that cause them to become charged. So that's the important thing to understand, that charge is conserved. So when you scuff your feet on a carpet in the winter and you pick up electrons from the floor, so your body becomes negative, the floor becomes positive. Again, conservation laws are important. Momentum is conserved, energy is conserved. Well, so is electric charge. So when one object gains charge, something else is losing charge, and vice versa. Now, we have to talk about this so we can do math, so we have to have a unit. Charge is measured in coulombs. Oh, I forgot a word there. It's measured in coulombs, which is abbreviated with a capital C. A coulomb is a very, very large charge. 1 coulomb is equal to 6.25 times 10 to the 18th electrons. It's a fairly large amount. What you may have heard of in your everyday conversations about the world is a coulomb per second, which is an amp. And when we get back to current electricity, we'll spend more time with that. If we need to then talk about the charge on a single electron, well, that's going to be the reciprocal of this number. So if you put 1 over that number, you get 1 electron is equal to 1.6 times 10 to the negative 19th coulombs. This is called the elementary unit of charge. In other words, that's the smallest amount that you can have. So if it's a positive E, that's what 1 proton would have. A negative elementary unit of charge is what a single electron would have. So understand that I can gain and lose multiples of that. For example, 1.6 times 10 to the negative 19th coulombs is possible. That's 1 electron. 3.2 times 10 to the negative 19th coulombs is possible. That's 2 electrons. 4.8 times 10 to the negative 19th coulombs is possible. That's 3 electrons. What I can't have is something like 5.0 times 10 to the negative 19th coulombs. Can't have that because that would be like 3.2 electrons, and I can't have 0.2 of an electron. I either have a whole electron or I don't have an electron. So let's look at something. Let's say something has an extra 6 million electrons. You've scuffed your feet on a carpet. You have an extra 6 million electrons. What's Q? And by the way, in equations, we use Q for electric charge. Measured in coulombs, but we use Q in the equations. So now, 6 million electrons. Well, instead of million, let's go 6 times 10 to the 6th electrons. Now, I want to get rid of electrons. I want to get coulombs. So what I need now is to make that fraction equal to 1. I can use either number. I can go the 6.25 times 10 to the 18th down here, and that's equal to 1 coulomb. When I multiply out, the electrons are going to cancel out. I'm left with coulombs, and I'm going to get 9.6 times 10 to the negative 13th coulombs, and that's negative since it's electrons. So that's kind of important. Now, let's look at what happens when objects interact. There's two ways objects can interact. Let's go non-touching first. So what I want to do now is I want to make things not touch. So let's say I have my finger. And my finger is charged negatively. I've scuffed my feet on a carpet. I have a bunch of negative electrons. They hate each other, so they've spread out, so they've gone to the surface of my body. I'm going to come near a metal doorknob. And this is metal. Metal's kind of important because electrons can move easily in the metal. Well, what's going to happen now, let's go to a different color. What's going to happen now is we know that negatives hate negatives. Negatives love positives. Well, since the only thing that can move is the negatives, what's going to happen is you're going to have positives and negatives here. But what's going to happen is some negatives are going to migrate over here. Well, if negatives migrate over here, then the net effect on this end is this side becomes positive, that side becomes negative, but the whole object is still neutral. I haven't touched it yet. Now, what happens is if I continue to move closer, eventually what's going to happen is I'm going to get negatives jumping. And now what's going to happen is it's no longer going to be neutral. Now it's going to have a net negative thing. And once the negatives get on there, the negatives are going to equally spread out. This is what happens when you scuff your feet on a carpet and touch a doorknob. What's going to happen now is the electrons can jump. And they can jump through the air if there's enough of them. It's the same thing with lightning. You get negatives on the bottom of the cloud, the top of the trees, or tall people become positive, and what happens eventually is when the difference is big enough, negatives will jump down, and that's kind of how lightning happens. Now let's look at touching, because this is a common thing they do on the AP test. By the way, touching is called conduction, so this is called charging by conduction. So what I'm now going to have is I'm going to take two metal spheres. And on this one, I have 4 microcoulombs. Now, the reason we use microcoulombs a lot and nanocoulombs a lot is a coulomb itself is an incredibly large amount of charge. So micro means 10 to the negative 6th. Nano is 10 to the negative 9th. But again, they'll give those to you. They don't expect you to memorize those. What I'm going to do now is bring it near and touch a neutral one. So what I'm going to do now is bring this over and physically touch it. So I'm going to slide it over here. Well, what's going to happen is since they're metal, electrons move freely. So what's going to happen right now is I got a bunch of extra negatives on here. We'll make that a negative. What's going to happen is those are going to go over here. If I then separate it, what I have is 2 microcoulombs, negative, and negative 2 microcoulombs over there. So I bring them together. Electrons are going to flow that way until they're equal. In reality, what's happening is there's probably some localized electrons moving back and forth when they're touching. Now, as soon as they're not touching, it's then going to split out equally. So there's a lot of things that you can do with this. Key thing to remember is that charge is conserved. If something is gaining electrons, something else is losing electrons. So therefore, if one object becomes positive, one object becomes negative. In the example up here, I don't know how that became charged with 4 microcoulombs. But somewhere else in the world, if this is negative 4 microcoulombs, there's something else in the world that's positive 4 microcoulombs. The way dryer sheets work, for example, is dryer sheets are positive. They come out of the box and they're positive. So what happens is, as they tumble around in your dryer, what's going to happen is they're going to suck up the extra electrons. So the extra electrons which are floating around in your dryer or trying to be transferred between articles of clothing in your dryer, those extra electrons are going to stick to here until eventually this becomes neutral. When that becomes neutral, it's not going to work anymore. That's why your dryer sheet's only going to work for 1 or 2 loads in the dryer. Usually at least 2 loads before you have to change it, although some people just change it with every one. It's also got some smelly good stuff in there and all that to make it better. But it's physics at work right here with dryer sheets. We also use this for pollution control. They will attract neutral dust in smoke, and by a large charge plate. They're called ionic air purifiers or electrostatic precipitators on a big scale. So we do use this stuff. Key thing is charge is conserved. They move freely in metals. Electrons move freely in metals. They don't move freely in nonmetals. So don't move freely in nonmetals. Most of the things when we talk about static electricity, we're usually talking about non-metallic stuff. Rubber balloons, your hair, stuff like that. They're not really that free to move in there, so once they get there, they will stay charged up until you get rid of it. By the way, if you want to get rid of static in your hair, put a dryer sheet in your purse. Unless you don't carry a purse. I don't carry a purse. Okay, have fun.